Good morning to everybody. So we continue quantizing Teichmüller space, which is represented by the basic algebraic system. Quantum Teichmüller theory. So recall that we are dealing with the basic algebraic system given by three objects, V, R, W, where V is the first open quadrant of the real plane. R is a map from V to itself given by x1, x2, to x2 minus 1, x2 minus 1, x1. And the W is a map from V squared to itself, given by x, this is x. If there are no indices, these are two objects, two component objects. And we have two binary operations. Today I'm going to write them because these will be the main objects to work with. So x dot y is given by x1, y1, comma, x1, y2 plus x2. And the x star y is two fractions with one and the same denominator given by the second component here. And the numerator here just bilinear term downstairs with 1, 2 exchanged. And here just we pull up the y component of the. So these are the operations. And we have a symplectic structure which is preserved by these operations. So omega v is the dx2 wedge dx1 divided by x2 x1. And for omega v squared, we take just the natural symplectic structure on the product of symplectic spaces given by pullbacks by two projections of omega v. Okay, so that's the working object. And last time we quantized the part V R omega V, right? With the result. So what was the result? Yeah, so we associated Hilbert space to object V, to two-dimensional R is a Hilbert space. Was identified as a space of square integrable functions on the real line, which is not surprising because of that symplectic structure, which is in logarithmic coordinates, just the standard symplectic structure on the real plane. And we constructed a unitary operator in that space, given by explicit formula. There are different ways of writing it out, but here is one way. 3 pi I q hat squared times pi I p hat plus q hat squared, where zeta is any number which gives -1 at power 3. And today we are taking the rest. So we will working with a W operation. Of V squared, W, and omega V squared. And as we outlined on general grounds, that quantization consists of two steps. First step corresponds essentially to what people do in deformation quantization. And the second step concerns the symplectomorphism itself. So the first step here is almost nothing to do, because we did almost everything last time. So we define how was denoted the algebra. I think we put just sub-index H bar, right? The algebra. We define algebra V squared H bar. Let me put in the parentheses as a V sub H bar tensor V sub H bar. Okay, V sub H bar was defined last time. So let me recall, where V sub H bar is generated by x1, x2. Actually, plus minus 1, right? Last time I forgot to say this, that they are invertible. But anyway, this is not a big mistake, I think. E I H bar x2, x1. And here, H bar is a quantization Planck constant. Okay, that's what concerns the algebra. And then we have to define W in parentheses sub H bar, which is an automorphism of that algebra. So we define and algebra automorphism which maps V squared sub H bar to itself. And we define it the following way. So W minus 1. If you remember the general formulas for quantization, we had to put somewhere minus 1 in order to take into account reversing of composition when we pull back forms, right? When we induce a transformation on the level of functions of forms, we reverse the composition. That's why we have to put minus 1 at some stage to preserve the homomorphism structure. And then we just say that where go the generator. So we have to say where goes this guy sitting in there, where goes this guy, and we say that this pair goes to x1 tensor x2, comma, x1 tensor x2 plus x2 tensor 1. So what I'm doing here, I'm just rewriting this, putting heads and inserting tensor products. Right? So y's live in the second component. So we have two coordinates on v squared given by x1, x2 corresponding to the first component v, y1, y2 corresponding to the second component of v. And that means that x's here should be living in the first tensor component over there. And y's here will be living in the second tensor component over there. Okay, so yeah, so here maybe I should say that x1 gets quantized to x1 hat tensor 1, x2 gets quantized to x2 hat tensor 1, y1 gets quantized to 1 tensor x1. But maybe it's not very natural switching notation, but x1 hat, x2 hat, they quantize just one couple of x1, x2 in V when we considered just one copy of V last time. So I'm referring to those x1 hat, x2 hat. While here we are considering two copies of V. So with coordinates called x and y. And now I'm just switching notation, but using the same copy of x1 hat, x2 hat, which quantizes one copy of V. Okay, so that please keep in mind this transition from notation. And then if you accept this, and then you just rewrite x1, y1, where it goes. It should go to where goes x1, which is x1 hat 1, right? And the image of y1, which is 1 times x1. And then, but we have to multiply in the tensor square of an algebra. And we multiply them by a component wise, which becomes like this, right? That's why we are. Here is a mistake. So that's the way it goes, and likewise the other terms. Okay, so now as concerns the second part, this is more tricky, but life is not that hard, even here, because of nature of the fractions there, structure of the fractions, and so here is the answer. So x2 goes to x2 in the first component. Y1 goes to x1 in the second component. Right? That's for the numerator. And we have to divide it by the denominator, which is given here already. But we usually don't write fractions for operators. We put -1. So that's what we do. x1 hat tensor x2 hat plus x2 hat tensor 1 -1. That's for the first component. And for the second component, y2 goes to 1 tensor x2 times the same denominator. And we have chosen some ad hoc order of multiplying numerator with the denominator. And, but there is a reason for that. So that will be the first remark. Today is lecture number 8, remark number 1. So the ordering problem here is easy. Why? Because they are relevant operators are commuting. What I mean by commuting, I mean that this guy here and this guy here, they commute between themselves in our algebra. For example, x2 hat tensor x1 hat commutes with x1, x2, and x2 hat tensor 1. So the second commutation is easy because x2 commutes with itself and x1 commutes with 1. But the first commutation is less trivial because x2 does not commute with x1. But if you pass through first x2 through first x1 here, you will get the phase e power minus I h bar. While on passing the second x1 through second x2, you get the phase inverse. And two phases cancel each other. And that's why they are commuting. And etc. So you can check that one tensor x2 commutes with any of those. This is easy. You see the 1 commutes with x1, x2 commutes with x itself, and here just the commutation with one of x2s. So no ordering problem. We can put either to the right-hand side or left-hand side. It will be just the same. Okay, and the second remark, 8, 2. So the triple V sub h bar, R sub h bar, W sub h bar is a basic algebraic system in the category of vector spaces with tensor product, but I put a hat to indicate that this tensor product is extended extends the algebraic, where tensor hat extends appropriately extended algebraic tensor product. Because as you see, we have to invert, for example, this guy, which doesn't live anymore in the algebraic tensor product. So this hat should take into account those. But I don't know. Honestly, I don't know how to formalize this. But anyway, that's what I mean by putting hat, because of the inverse. But this is not very important. But anyway, just to keep in mind on what we're doing on the large scale, seen from the height of airplane, right? If we look on the ground, we don't see much details, but we can see a basic algebraic system in the category of vector spaces. And there is one more remark. (8.3), which tells the following thing. So, which is a particular case of the previous remark. In particular, how to put it? Yeah, the operation. The operation delta, which maps V sub h bar to v sub h bar tensor v sub h bar. I write it explicitly, given by delta w minus 1 sub h bar. Yeah, so let me put delta of A is given by, let me put hat, w minus 1 sub h bar, A hat tensor 1 for any A hat in V sub h bar. The operation, some of you can recognize it. Gives rise to a Hopf algebra structure. Structure in V sub h bar. Coinciding with the Borel subalgebra of UQSI2 with Q equal EI h bar. So this is a very interesting remark because a priori we never used any Hopf algebra idea in our research. We started just from Teichmüller space, if you remember. At some moment, we identified the Ptolemy relation on changing the triangulations. And we also remarked the presence of Weil-Peterson symplectic structure in Teichmüller space. And we went on just doing some algebra or transformation. And just at the stage of first step of quantization of W function, we all of a sudden recognized the appearance of a coproduct. So so x1 just becomes k, and the x2 becomes e, right, in the Hopf algebra. And so that means that so Ptolemy couldn't discover quantum groups because he didn't know what is Weil-Peterson symplectic structure. Okay, so that is it. The first step is accomplished. And now we turn to step number 2. So what we have to do, if you look at the general outline of the quantization procedure, on step 2 we have to pick up a Hilbert space. So we choose Hilbert space. Space V squared to be space of L2 functions over R2. If you remember, we had a the Hilbert space associated to one copy of V, just L2 of R. Now we have to do something, some tensor product operation in on the level of Hilbert spaces. Hilbert spaces are completed vector spaces. So instead of putting just algebraic tensor product, we double the number of arguments in the functions which represent elements of that space, which naturally extends the algebraic tensor product of L2 of R. Right, so this choice looks natural. And the next thing, we pick up realizations. And we realize x1 hat tensor 1. So that's what we have to do. And we realize these guys like E 2 pi B Q1, x2 hat tensor 1 is realized as E 2 pi B. So I'm writing equality, but if you want to be more formal, you have to say that some map into operators, right? So let me just ignore this formality, just equate them. 2 pi B P1 hat and 1 tensor x1 goes to E 2 pi B Q2 and 1 tensor x2 becomes a E 2 pi B P2. So B where h bar equal 2 pi B squared as we wrote last time. And P J, let me put J, Pj and Qj are Heisenberg operators. Heisenberg operators. Let me put it this way. So X Qj. So X by definition is a two-component things, right? I'm using the Dirac bracket notation. So bravector with a label X means a vector with two components. We are now in L2 of R2. And if we act by Qj hat, this will be Xj multiplies X. And if we multiply act on X by Pj hat, this will be 1 over 2 pi I d over d xj applied to X. And now you see why I put J, not I, just to avoid the confusion with imaginary 1. Because both are entering here, and J lives in the set of two elements, 1, 2, and I squared is minus 1. Okay, that's the realization, and this is naturally almost no choice here, right? So if we accept what we did last time, then we just put the same formulae in two tensor components, nothing more. And this satisfies commutation relations. So Heisenberg operators satisfying commutation, Heisenberg commutation, Heisenberg commutation relations in two dimensions. So here I'm referring to physical two dimensions, so which means that we are dealing with a particle in a two-dimensional space. So Pj hat commutes with Qk hat as a delta jk divided by 2 pi I, Kronecker delta, and all other commutators are trivial. So these are the extension of Heisenberg commutation relation in one dimensional space, which was just one copy of P and Q. And here we put the same thing for each coordinate axis, as we did for one real line. And then two different axes do not interact at all, in the sense that the corresponding operators commute. Okay, so that's first part of the second step. And now everything is fixed, right? The framework is fixed, or saying differently, the rules of the game are fixed. Now we will play the game. And the playing the game means the calculation of the quantum operator corresponding to W transformation. Calculation of the operator hat. So what are the equations to solve the equation? Equations to solve are to solve or to be solved. To be solved are as follows. So what we put, W hat minus 1 conjugates A hat and gives the image of W minus 1 sub H bar applied to A hat, to any A hat in the quantized algebra V2 sub H bar. Right? These are the general formula. But usually we remove minus 1, but I keep minus 1 because all our formulas are written for minus 1. But of course we can invert it and rewrite it for W put without minus 1 here, so we can replace it. But then we have to change, rework the reverse map. But let us keep the same map. It's invertible anyway. And we here we add that in fact it suffices to consider only 4 cases with A hat living in E 2 pi B Q J hat and E 2 pi B P J hat for J in 1, 2. And we use one and the same formula here, where a hat is taken to be any of them. And it will be clear a little bit later, in a moment, why it is so. And now we have explicitly write out those equations. And explicitly, we have. So let us write the case A hat equal E 2 pi B Q 1 hat. So then what we have, W hat minus 1 E 2 pi B Q1 hat W hat should be equal. And now we should look at the formula so which we wrote some time ago. And we write the image of that guy under that automorphism, which is E 2 pi B Q1 hat tensor E 2 pi B Q, no tensor, right? Now the tensor is replaced by indexation 1 and 2. E Q2 hat, right? That's the formula. And now using the fact that this is equal to 2 pi B Q1 hat plus Q2 hat, because they commute between themselves, so we can put both of them together in the exponent. And now we can profit of linearization as we did last time. If you remember, the operator R was acting eventually linearly in the space of P and Q operators. And in this particular case, for this particular equation, we have the same property. So we can just take logarithm of that. So this is equivalent to saying that W hat minus 1 applied to Q1 hat by adjoint action is equal to Q1 hat plus Q2 hat. Right? So we, if you want, we just insert this W in the argument, and then we just take a logarithm. These are positive real operators. So logarithm is a one-to-one operation. So we end up with this first equation. And then for A hat equal E 2 pi B P1. So on the left-hand side, we get W minus 1 conjugates E 2 pi B P1 hat W hat. On the right-hand side, we write the formula. I just write the answer, and you just check that it is correct. Plus Q1 hat plus P2 plus E 2 pi B P1. And here is the difference with what we had last time. We cannot take logarithm anymore here, because the exponentiation mixes up with addition. And it's easy to take the logarithm on the right-hand side, but of course we can take the logarithm of that still positive operator. But it doesn't make much sense, because first of all, these two operators do not commute between themselves. And now they're taking, so we can make sense of it only in the spectral sense, but so far we don't know, we don't want to go right away to spectral picture. So we keep this equation as it is. And now let's go on. Two more cases. A hat equal E 2 pi B Q2. So then in the left-hand side, we have E 2 pi B Q2 conjugated by W inverse. On the right-hand side, we write out the answer. So what did we have there? I think we had E 2 pi B. No, I don't remember. So x2 becomes q2 plus x1 in the second. Yeah, this x1 in the second and x2 in the first. P1. And times, that's inverse, right? So let me, because this is not a nice guy, just for the reason I said a moment ago. It's not nice with respect to taking logarithm. But the left-hand side of that is nicer in that respect. So let us use this equation in here just to remove the inverse of that. And we put instead inverse of that. So we just put w hat minus 1 inverse minus 2 pi b p1 w hat. And now we can multiply both sides by inverse of that to remove it from here. And we immediately see that we can take a logarithm easily. So this becomes a w hat minus 1 conjugates q2 plus p1 and gives, again, q2 plus p1. So let me put in a frame nice-looking formulas. And last case, E2 pi b P2. So W inverse E2 pi b P2 hat W hat. And on the right-hand side, we have to put what we have to put, x2 in the second component, P2. E2 pi b P2 hat. And the same thing, right? So I put that guy. Same trick and same transferring of that guy to the right-hand side. And we end up that this equation is equivalent to w hat minus 1. So this P1 gets combined with P2. P2 hat plus P1 hat, W hat, is equal. What remains here is P2. So these are equations to solve. Let me call them equations for W. And we can enumerate them. Equation number 1. Let me now surround this equation. It's equation number 2, 3, 4. And after the break, we will be solving the system of those 4 equations. But before, we will be making a little preparation to justify why it suffices to consider only 4 equations out of infinitely many. And that we will start by justifying this part and then turning back to these 4 equations. Okay, now we make the break. So before we continue with the system, so we are going to make a little break and spend some time on general things. Okay, let me start by lemma 8, number 1. So last time we had a couple of lemmas. Today we will have again a couple of lemmas, but only one of a very general nature. So here it is. So let A be an operator in L2 of R. So we are back to L2 of R because the essence is already visible on the level of L2 of R, but we will be applying using it in the context of L2 of R2. But anyway, so we operate in L2 of R such that its integral kernel is a tempered distribution. Then there exists a unique tempered distribution f sub a hat acting from R2 to C. So I say by words a tempered distribution, but write it like a map, as we do usually, right? We think of distributions always like functions, even if they are not. Okay, a unique tempered distribution such that operator A is written as the integral over R2 f a hat of xy e 2 pi I q x q hat e 2 pi I y p hat dx dy. Okay, so how to prove it? Let us see. Proof. So we just take the integral kernel of both sides. So if equation star is true, then it means, okay, let me say it differently. So the star means that the integral kernels are equal. Okay, so u a hat v is equal to R2 f a x y u e 2 pi I q hat x e 2 pi I p hat y get v dx dy. That's the meaning of that equation usually. So, and we always can think about operators as given by their integral kernels. Right? To avoid working with abstract operators in abstract Hilbert spaces, we can just realize our Hilbert space as a square integrable functions on some measurable set, as we have here. Then we can just talk about integral kernels as equivalent things about operators, like here. And then what we do, we just work out this equality. It's a consequence. So what we have here. So first of all, q hat hits its eigenvector. So this becomes e 2 pi I u x times u e 2 pi I p hat y v, right? And then p hat hits u, and it is a translation operator. right? It's a unitary translation operator. So this is equal u plus y bracket with v. And this is the delta function. Delta function u plus y minus v. And now we can just, by using this, we can remove one integral because there is one delta function which contains one of the integration variables. So the integral becomes one-dimensional, f a hat xy e this guy 2 pi I ux. This delta function, okay, so the delta function removes y. So y becomes v minus u, x v minus u, this exponential 2 pi I u x. Delta function has gone. And that's it, dx. So the integral kernel of A is equal Fourier transform of that kind. And the Fourier transformation is with respect to variable x with new variable u. But u enters twice, also in the second argument. So let us remove it just by shifting v by u. So we rewrite this as a u bravector u a hat ket v plus u is equal. So I just rewrite the obtained formula, integral over r f sub a hat of x v, right? Now u disappears after the shift here, e 2 pi I u x dx. Now it is a true Fourier transform of function of unknown function f with respect to the first argument. And the second argument is just kept fixed. So we can solve this by taking inverse Fourier transform. So this is equivalent to f of xv a hat equal inverse Fourier transform. So we write this integral kernel a hat v plus u e minus 2 pi I ux du. And now why we need things to be tempered distributions? Because otherwise we cannot make sense of the Fourier transform. And actually, at this moment, here comes a remark concerning the lemma we proved last week. We didn't precise that the function in lemma 7.1. We didn't precise that the functions involved functions. No, in lemma 7.2, I think, where we used the Fourier transformation. Let me see. Yeah, so in lemma 7.2, we have to add that the functions should be at most polynomial growth, right, to make sense of the Fourier transforms or tempered distributions in lemma 7.2. Because if you look in the proof, we use the Fourier image of function g. Right? Maybe the lemma is true in that generality, but we proved it only for that case, and as we do here. So, but here I realized this fact. Last time I didn't. Okay. Please add then in the assumptions this condition. Okay, let us just work out an example. Yeah, okay, we will restore this anyway. Example, so let us take a hat to be operator Q. So what is the function sub of fq? Then f sub q of xv, what is it? So integral, we have a kernel u q hat v plus u e minus 2 pi I u x du. So we know what is q. It pulls out like u, delta function u minus v minus u, e minus 2 pi I u x du. So as you see, u goes away from the delta function. So delta function is u independent. It pulls out the integral. And then in the integral, so how we treat this u usually? Usually we realize as a differentiation if we see an exponential. So it is written like I over 2 pi d over du dx acting on the exponential minus 2 pi I ux du. And then we pull out of the integral because it is u independent. So vi over 2 pi d over dx. And what remains as integral, it's a delta function of x. Delta function of x. So it is I over 2 pi delta of v delta prime of x. That's, as you see, it is given by a distribution, not only tempered, but of compact support. Right? It's localized just at the origin of the plane. So how this lemma works. Now we get back to our system, solving system EW. And we start by solving the simple part. Let me put it lemma A2, which tells that the equations okay, so maybe I should, I promised why considering 4 equations are enough, right? Let me put this as a remark here. So in that case, so in the context of that lemma, we will write a hat to be a hat of QP. Right? So if we have just one single operator, which is self-adjoint to be able to apply spectral theorem, then we can write a function, a measurable function of that operator. That's no problem. But now, due to this lemma, we can write an operator as a function of 2 even non-commuting PQ by meaning that integral decomposition. Right? And then we will treat this as a true function, but always keeping in mind that behind of it's this integral formula. And now, why it suffices to have 4 equations in the system for the operator W? Simply because if we write for unknown operator W this integral formula, then it will be function of two pairs of Heisenberg operators, and then those 4 equations will treat dependence of those with respect to those 4 arguments. We will see how this works in our system. Okay, that's a vague explanation why we are sticking only with 4 equations out of infinity. Okay, now going back to lemma 82. So equations EW with numbers 1, 3, 4. Right? We forget for the moment equation 2, which is complicated equation, nonlinear. And this 1, 3, 4, they were linear. Have general solution of the form W hat of W hat equal phi of Q1 minus Q2 plus P2 exponential minus 2 pi I P1 Q2 for some function phi in from R to C. So that's the first part of solving the system EW. So 3 equations out of 4 fix the operator up to a functional ambiguity. For any, actually, sorry, for any function phi is not fixed by 3 equations 1, 3, 4. So let us prove it. So what we start by remarking that we have E2 pi I P1 hat Q2 hat. So this is a unitary operator. And if we conjugate Q1 by that operator, then by Baker-Campbell-Hausdorff, for example, we observe that this is equal Q1 plus Q2 hat. And likewise, if we conjugate P1 hat plus P2 hat, right? So that's the same thing. We conjugate by the same thing, we get a P2. So that, and maybe I should add and P1 plus Q2 same thing, right? Equal P1 plus Q2. Because P1 commutes with Q2, Q2 commutes with P1, so nothing happens here. So that the operator S hat defined by W hat times E inverse this operator, 2 pi I P1 hat Q2 hat. Operator satisfies the equations. So let us see. So equation number 1. So it was W hat minus 1 Q1, W, it was equal Q1 plus Q2. right? That was the equation. Let me check. Yes. And now we can write it, this Q1, Q2, like this. Q1 and now we can put this operator together with W, so this becomes S hat Q1 hat commutes trivially, right? Because we put all together, W converts into S hat together with this. So you, look, for example, if we multiply by inverse of that, here will be S, here will be S minus 1. So S minus 1 conjugate Q1, it gives Q1, which is equivalent to commutation relation. And now, this means that S hat equal S hat. So a priori, we would write like this. Right, due to integral formula. And but the commutativity condition with Q1 eliminates the dependence on P1. So this is equal S hat of Q1, Q2, P2. So you see, it, the one equation specifies dependence of our operator by reducing the number of operator arguments by 1. So and this is due to lemma 7.1. Because here the second space is not concerned. What concerns us only the first subspace. And in the first subspace we have a copy of L2 of R. And now lemma 1 tells us that if some operator commutes with Q1, then it is a function of Q1 only. That's why P1 drops out. So here we have a structure as a consequence of the first equation. Now the second equation, which is a third actually. Third means S hat. It's just this part. S hat commutes with P1 hat plus Q2 hat. And now how to treat this? So by P1, by using P1 hat plus Q2 hat equal, what is equal to E minus 2 pi I Q1 hat Q2 hat P1 hat E 2 pi I Q1 hat Q2 hat. So we can get this operator by conjugating P1 by some unitary operator. We rewrite as so we just conjugate this by this operator. So E 2 pi I Q1 Q2 hat S conjugated by this commutes with P1. So we got that some operator commutes with P1 hat, which means that so if I call this operator A, right? Then so by lemma 1, still same lemma, A hat becomes a function of P1, but no Q1, Q2, P2. The same argument as in the previous case, but now we can translate this into a conclusion for operator S. So equivalently, S equal E. So we have to conjugate back the operator A. Minus 2 pi I Q1 Q2 A E 2 pi I Q1 P2, which is now, I keep this functional notation. So we conjugate P1, which becomes P1 plus Q2. We conjugate the first argument by this guy. So it gives P1 plus Q2. Next, Q2 doesn't change. This is Q2. Q2 doesn't change, and P2, what happens to P2? It behaves like this. So P2, we add to it a Q1. Right? And now we say that so W EW1 plus 3 is equivalent to the fact that S hat depending on Q1 hat Q2 hat P2 is equal another function A hat of P1 hat plus Q2 hat Q2 hat P2 plus Q1 hat. So when the equality is possible, so first of all, we see that in the left-hand side there is no P1. But in the right-hand side there is P1. So we cross out this due to lemma 7.2. Right? If a function depending on Q1 equal to a function depending on P1, then we no, sorry. At least this does not depend on P1, right? So we cross out, but we cannot cross out Q1 because Q1 shows up elsewhere. So we cross out P1, and then we want to achieve a structure. So Q2 here so P2 enters to dependence only through combination Q1 plus P2. So that means that S hat becomes a function of only two arguments. Q2, or let me put Q1 plus P2 and Q2. Right? The conclusion of this equality is this. So we cross out this, and then we end up with only two combinations. Okay, so we used two equations. We reduced the number of arguments by 2. And then we go on. We have one more simple equation, EW.4. So what is it? So EW4 is equivalent to S commuting with P1 hat plus P2 hat. But we can rewrite this. The P1 hat plus Q2 hat can be rewritten P2 as a conjugation by E minus 2 pi I Q1 hat P2 of P1. So I'm doing a similar thing as before. So I'm bringing by unitary transformation the operator with which commutes our operator to one of the operators P1 or Q1 in order to apply subsequently lemma 7.1. So we do this, so which means that E2 pi I Q1 P2 S hat E minus 2 pi I Q1 P2 commutes with P1. So which is equivalent by lemma 7.1 to, so let me call this B. Notation just B hat becomes a function of only P1 and Q2 P2. Right? We conjugate it back. So S hat becomes E2 minus 2 pi I Q1 hat P2 B hat E 2 pi I Q1 hat P2. And what is this? P1 becomes P1 hat plus P2 hat by conjugation. Q2 becomes Q2 minus Q1. And P2 doesn't change. And this should be equal to S hat plus EW 1 plus 3. Right? This should be equal to that. Q1 hat plus P2 hat, Q2 hat. And what we see here, first of all, P1 should not show up at all. So we cross out this part. And we see that P2 should enter in the combination with Q1 plus P2. And so that ends us with only one possibility, that S hat is S hat of Q1 plus P2 and minus Q1. Right? So, and this is the phi of. Now we can think of true functional argument because we ended up with one single operator argument. Now this is not formal anymore, just one single operator argument of phi. That ends the proof of lemma. And effectively, what we did just linear algebra on the level of Heisenberg operators. And the interesting part now is squeezed to equation 2. And this will be, as it is the most important part, it will be a theorem. Theorem 8.1, which tells the following thing. So any solution of a system EW is of the form W hat equal phi of, this is a lemma, right? So there will be Q1 minus P2 minus Q2, E minus 2 pi I P1, Q2. But now phi is not arbitrary function, where phi is a function from R to C
Plus P2.
Yeah.
Sorry?
Plus P2.
Yeah.
Plus P2, thank you. Yeah, of course. So phi is a admits, yeah, function where phi admits analytic continuation into the strip, imaginary part of Z less than B, or B like this, and satisfies, or where it satisfies, or maybe and, okay, and satisfies the functional equation. What is the functional equation? Phi of x minus IB over 2 is equal 1 plus E 2 pi B x phi of x plus IB over 2. Yeah, so let me put it here. Yeah, we can just leave it as it is. Maybe, because it should be invertible after all, right? So W by definition. For any x in R. That's this is a lemma, previous lemma, which is easy, and non-trivial part is concentrated in here, which comes out from equation number 2. So let us see how proof goes. So we keep this. W is given by star due to lemma 8(1), right? So we take with arbitrary, with unfixed phi, and then we turn to equation number 2. Equation number 2 is equivalent to. Yeah, so let us write it explicitly. So W, we write it. So let me put this S, for example. So S minus 1 conjugates 2 pi B P1 S equal. Now I put this part to the right-hand side. E minus 2 pi I P1 Q2 conjugates this exponential E 2 pi B Q1 plus P2 plus E 2 pi B P1. And conjugation 2 pi I P1 Q2. And now let us conjugate. That's not difficult. E 2 pi B. So Q1. Conjugation of Q1 corresponds to subtracting from Q1 Q2. Q1 minus Q2. P2, the effect on P2 is that we add P1 plus E2 pi B P1 doesn't change because P1 commutes with Q2 and itself. That's it. And now here I'm using a trick, the following. So I pull out, so as you see to the functional equation, we have a 1 here plus something. So we want to create 1, so which means that we have to pull out one of the factors. So we pick up this one, and we want to pull out it. But this guy doesn't commute with this. So the trick to avoid correction terms, we pull out one half to the left, another half to the right. So we write it 2 pi b P1. And here we just subtract P1. 1 plus E 2 pi b Q1 minus Q1 minus Q2, or plus P2 minus Q2. E pi b P1 hat. So why this formula is correct? So if we multiply both sides, so 1 reproduces this term. But here we have to use Baker-Campbell-Hausdorff twice to add the two guys. But when we put this into this exponent, we take one commutator with sign plus. And we take, when we put another copy of that, we take same commutator with the minus. So the corrections coming from Baker-Campbell-Hausdorff cancel each other. And this is due to symmetric pulling to two sides. Okay, so we have this equality. And it remains just to put the exponentials of P1s to one side and write out explicitly the S formula. So E minus pi b P1. So now S inverse, which is the inverse of phi, which is Q1 plus P2 minus Q2. E pi b P1, E pi b P1. So I put in two copies. So I split these two into, this is minus 1. Phi of Q1 plus P2 minus Q2. E minus pi b P1 equal E1 plus E2 pi b Q1 plus P2 minus Q2. And this is equivalent to, now we can apply a unitary transformation to pull out all dependence on the second argument. And so this becomes just the identity in L2 of E pi b P, E pi b P, phi of Q, E minus pi b P, equal 1 plus E2 pi b Q, right, in L2 of R. And as you see, what we have profited of, we have profited of the fact that the phi has been identified as an arbitrary function of one single combination of Heisenberg operators. And the very same combination appeared in the non-homogeneous part of the, in this known part of the equation. And this reflects the consistency of our system, or saying differently that we were solving a system of equations coming from the true automorphisms of the algebra. And this is the reason why we didn't come to any contradiction and stayed consistent that the argument which we have identified happen to be the same as here. And now we can, so formally, we can just apply Baker-Campbell-Hausdorff. And then due to the reality of these exponentials, so this becomes a phi of q plus pi b divided by 2 pi I. Right? And then and here with opposite sign. Phi of q minus pi b over 2 pi I. So this effectively ends up the proof because we have arrived to our functional equation because we can cancel pi's. And our equation becomes exactly the equation we have written over there if we change q to just variable x. And so the only thing which remains to say why we should interpret it as in terms of analytic continuation, because this is the only way of thinking of complex shifts of real valued argument, right? And then this conjugation can be accomplished by starting the unitary conjugation, which is well defined, and then going analytically from unitary conjugation to real conjugation. And on the way, we have to go all in the complex plane, right, to make this real if we start from pure imaginary. So that's the only way of interpreting this complex shift. And or saying differently, we can think of this as an eigenvalue problem for positive operator given by this operator. And then just solving the spectral problem for this self-adjoint operator, we can come to the same conclusion to the construction of the operator S. Okay, so we have to stop here, and we continue discussing this functional equation next time.